Hello and welcome to Applied Electromagnetics for Engineers. In this module we will complete analytical solution of Poisson's equation in one dimension and then talk about numerical methods for solving Laplace's equation. We will concentrate on one method today called as finite difference method. Now Poisson's equation is applicable whenever there is a certain charge density. So the general expression for Poisson's equation is that del square V is equal to minus rho by epsilon, where rho is a charge density measured usually in coulombs per meter cube. Okay, epsilon is the material permittivity that we have. We will apply this Poisson's equation in order to solve for the potential and the fields of a very important electronic device known as a PN junction. If you remember from your solid state physics, or you might remember from electronic circuits, PN junction is formed when you bring P junction and the N junction close to each other. Of course, modern PN junctions are not really manufactured this way, but you imagine that in the olden days where P and N junctions were grown separately and then brought and made them contact, what would happen is that the charges would essentially migrate, right? Because of the diffusion, there would be excess positive charges in the P side or the holes, and these holes would migrate. Actually the electrons would migrate, but anyway it does not matter. So leaving behind immobile negative ions here, and the electrons would diffuse to the left hand side, leaving immobile positive charges. Now whenever you have a positive charge and a negative charge separated, there will be an electric field, and in this case the electric field is directed from the N side to the P side. Now you can't have this situation of uncovered charges or the immobile charges everywhere in the bar, PN junction bar. So it will actually happen over a very small region at the center of the junction, and let us consider for now that both P type region and N type region are doped sufficiently equally between the two, such that the width of the space charge region, as we would call this, the width of the space charge region is A in the N region, and it is the same A in the P region as well. And because the charge distribution is also symmetric, which is unknown, we do not know what is the charge distribution, and that is in fact one of the things that we would like to find out, or maybe in this case we do not really like to find that one out. This can be related to the doping profiles. So we have this charge distribution rho 0 which is uniform, and there will be a minus rho 0 charge distribution because negative ions carry actually negative charge. So this is the situation that we now have, and this is our expression that you need to solve this one. We will consider the solution of Poisson's equation only in the region x, in the N region, that is when x is greater than 0. The same results can be obtained, or the same results can be applied, the same method can be applied to solve for the potential and the electric fields in the region, in the P region as well. I will leave that as an exercise. And because this is a one dimensional Poisson equation, because of my simplification, I do not have to solve a partial differential equation. I can just solve an ordinary differential equation which tells you that d square V by dx square equal to minus rho 0 by A when you are in the N region. Of course, when you are in the P region, this will actually minus rho 0 will be replaced by plus rho 0, okay, because the charge density there is negative. Okay. Integrating this equation once, you get dV by dx equal to some constant minus rho 0 x by epsilon. So we will also need to integrate this one once more, right? So you will have to integrate this one once more. D square V by dx square will be some constant C1 x minus rho 0 by epsilon x square, okay? Or rather, instead of directly going to the and then adding one more constant over here, what we will do is we will first apply the boundary condition and then try to remove C1 right here itself. What is the boundary condition that I am going to apply? Well, dV by dx actually gives me electric field, right? So minus electric field is dV by dx, and at x equal to A, right, this electric field must be equal to 0, okay? So at x equal to A, dV by dx must be equal to 0. So when I put x equal to A into this expression and then set dV by dx equal to 0, I get C1 as rho 0 by epsilon times A. So I can simplify my life by putting this rho 0 A by epsilon into this expression and rewrite dV by dx as rho 0 by epsilon minus x minus A, okay, which again I am going to integrate, and next time when I integrate, okay, I will leave this as a small exercise to you to show that what I am writing is correct. When I integrate it again, I get V of x, which now is given by minus rho 0 by 2 epsilon because of x minus a there will be x minus a whole square and there will be a divided by 2 plus some integration constant C2. Okay. Again, what is the potential at the center of this one? The potential at the center, because the charges are just kept between the two, so at x equal to 0 the potential actually has to be equal to 0, which allows me to find C2 as rho 0 a square by 2 epsilon. Substituting this into the total expression for v of x, you can show that this is given by rho 0 by 2 epsilon 2ax minus x square. Okay, so this is the potential that you actually have. And what is the electric field? Remember, electric field is minus gradient, but in this case it is just a one dimensional thing, therefore this is minus dv by dx, and this is given by rho 0 by epsilon x minus a. Of course, the electric field is measured in volt per meter, and this is the electric field in the n layer. For the p layer you replace rho 0 by minus rho 0. Okay, and how does this electric field look like? So you have this as the x axis. So if I now plot electric field E of x at x equal to 0, you see that this is at the center and it will actually have a maximum value of the electric field. The maximum value of the electric field is actually negative. That simply indicates that the direction of the electric field is in opposite direction to x. Okay, so this is minus rho 0 by epsilon times a. At x equal to 0 this would be 0, the electric field, and on the p side region as well, when you replace rho 0 by minus rho 0, this becomes x plus a, but at x equal to minus a the sum will again go to 0. So the electric field that you have will have this triangular form. Okay, and the voltage that you are going to if you were to plot the voltage in the p and n region as a function of x, that will be like a saturated, it will have a linear plus parabolic kind of a thing. So far away from the junction it would be saturated, although this is strictly not speaking we have derived that one, but at the center it would be 0 and then it would go something like this. Okay, so far away from the junction the value here is rho 0 by 2 epsilon a square. Okay, so rho 0 by 2 epsilon into a square, and this is the same value here as well, rho 0 by 2 epsilon into a square. Okay, you can obtain this one simply by taking in the v of x at x equal to a. So whatever the value that you are going to get at a will essentially be the potential, because beyond that everything will be a constant potential term. Okay, so at x equal to a you can show that this would be equal to rho 0 by 2 epsilon a square. Now that we have potential as well as the electric field, we can also calculate what is the capacitance of the junction. The capacitance will be given by the total charge that is contained by one region or one particular side, divided by whatever the potential that we have applied, or rather the potential difference that we have applied. The potential difference that you are looking at between the two junctions, because v of x is positive here and v of x is negative here, the total potential junction is the difference between the two, and that is called as a junction potential. And for this case the junction potential happens to be rho 0 a square by epsilon. Okay, you can substitute that one here into the expression for the junction potential. The stored charge will be the amount of charge density that you have, rho 0, times the area of the bar, which would be a. I have not shown you the 3-dimensional case, but you can assume a uniform area a and a width of a. Only in this volume you are going to have some charge stored, or the space charge stored, divided by the junction potential, which was rho 0 a square by epsilon, and what you see is epsilon a by small a farad. Okay, this is like a parallel plate capacitor, so that we have actually obtained. Now here is an important thing. The cases that we have considered for Laplace's equation or Poisson's equation are actually quite small. There are not enough examples that we have considered, but even if I consider a list of rather large examples of how to solve these equations analytically, I still have only a very few cases, okay, of where complete analytical solutions are possible and closed form expressions can be obtained. In a simple scenario, if I instead of considering a coaxial cable with a circular cross section, if I make the cross section rectangular or elliptical, then the solution, the corresponding solution actually becomes very complicated. In some cases the solution does not even exist. This is an example of a microstrip transmission line, for example. The structure is actually very simple. You have a ground plane and then you have a certain insulator, and top of it you actually have a signal layer, Okay, but so far, despite lot of effort by lot of people, there are no complete analytical expressions for solving microstrip line impedances or other parameters of a microstrip line. The approach that we normally take in solving practical problems is to go for numerical methods. Okay, and what I would like to do is to introduce you to a very simple numerical method. For a proper application of numerical methods in electromagnetics, there are other courses in the same NPTEL MOOC this year. You are free to look at that courses to get a parallel idea of what difficulties you are going to experience when you apply numerical methods to electrical to solve for electromagnetic problems. But our focus is to give you an introductory idea of how to approach electrical for the electromagnetic problems using numerical methods, and towards that end I have picked the first numerical method, which is a very simple numerical method called as finite difference method. Okay, and what is this finite difference method? We are going to apply this finite difference method to the problem that we actually have already solved. That is, we have solved the problem of Laplace's equation in 2 dimensions for a square trough problem, right? The square trough problem is, if you imagine from the top view of this one, you just imagine that there is a kind of a rectangular sized bucket, and this bucket keeps on increasing. So this is my square trough that I am considering. Okay, so this is my square trough, and let's say these walls go all the way to infinity. So you can imagine a rectangular box with walls going all the way to infinity, but then I actually consider the cross section in such a way that this box, which has these 4 sides out there, has a certain small gap over here. Okay, these are the insulating gaps that I have, and one edge of this gap is kept at a potential say V0, and all the other potentials are kept at 0 volts. Okay, so we keep all these at 0 volt, and you have to simply imagine that this is just going on top. So what we want is the potential V of xy inside this trough region. Okay, so for our case we will simplify the problem saying that the dimension along z is not really important for us, it will be uniform, we will simply assume that, and what we want is the potential V of xy as well as the electric field inside this particular region. We already can, and we have shown what is the analytical solution, okay, for this problem. But what we want to do is to actually apply numerical method and see how well we do with respect to analytical method. The other advantage, as I said, about numerical method is that it is not restricted to only this problem. For example, if I consider this trough, okay, there is absolutely no simple analytical solution for this problem, but this problem can be as easily handled as the corresponding square trough problem. So that's the advantage of numerical method. So you can easily generalize it to other cross sections without too much of an effort. Okay, so the equation we solve is del square V equal to 0 subject to boundary conditions, right? So there are certain boundary conditions which we have given here. Subject to that, we need to solve this del square V equal to 0, and this we need to solve in 2 dimensions. So go back to what this equation is. This del square, if you expand in Cartesian coordinate, becomes del square V by del x square plus del square V by del y square equal to 0. If you have never seen a partial derivative before, okay, I do hope that you have seen, the partial derivative of V with respect to x, okay, is actually at some x plus delta x for a given value of y. So you have to find out along x at certain point x plus delta x, just a small step away from that at the same value of y minus V of x comma y, which is the potential at the point x y, and divide this one by delta x and then take the limit of delta x going to 0. Well, this is how mathematicians would define the partial derivative. And if you want to define what is the second partial derivative, del square V by del x square, then you have to consider limit of delta x going to 0, but not of the potential values, but rather the derivative of x, partial derivatives themselves. So d square V by dx square can be written as d by dx of dv by dx. So instead of any function, you just take dv by dx or del v by del x itself as a function and evaluate that del v by del x at 2 different points. Okay, so you evaluate del v by del x at x plus delta x minus del v by del x at x, divide the whole thing by delta x. Now you apply one definition for del v by del x at x plus delta x itself by using this above expression, right? Let me clarify all that by actually drawing a line. Okay, so this is the x axis. So I am going to draw some grid points as we would call, and then mark this as x comma y. Okay, and since I would like to give some numerical this one later on, I will call this as x1 y1, I will call this as x2 y2, and then I extend this for once more, call this as x3 y3. I will assume that all these are equally spaced by an amount of delta x, okay, or by an amount of h being more used than delta x. So I am assuming that every grid point is actually with a spacing of h. Even the top lines or the horizontal lines are spaced by the same value of h. There is no restriction that this has to be this way, but it simplifies our introduction to the methods. Okay, in practice you do not have equal grid separation. There are regions where you want higher accuracy, so you actually discretize at a much finer size, and then when you don't really want accuracy or the function is not really varying much, then you use a larger value of h. But those are implementation aspects, we won't get into the details out there at this point. So I need the partial derivative at say x1 and y1. Okay, so in order to obtain the partial derivative at this particular point, I need to find out the slope here and the slope here, and then subtract the slopes and then divide this one by h. Okay, so how do I do that? I have already seen. So these are the slopes. So this is the slope at x1, this is the slope at x2. Okay, so what is the slope at x1? That is nothing but del v by del x while keeping y fixed. Okay, so in along there is a small mistake which I did. So this is actually the point x2 y1 x3 y1, because this is the line where y is equal to y1, this is the line y equal to y2, and on top there will be another line y equal to y3 and so on. Okay, this line is x equal to x1, x2, x equal to x2, x equal to x3 and so on. Okay, so this is x1, x2 and x3. So the slope at x1 is essentially this del v by del x while keeping y fixed at y1. Okay, and this can be written as v of x2 comma y1 minus v of x1 comma y divided by h, right? So I get the value of x potential at this point and the potential here, and then divide this one by h. Now I don't take the limit. Why don't I take the limit? Because on a computer I can't take the limit of 0, right? So all numbers on a computer are represented by a finite value, and I can't take h to go to 0. So on a computer this is what I am going to have. So this is the slope at x1. Similarly, the slope at x2 will actually have v of x3 comma y1 minus v of x2 comma y1, right? So the slope at this point will actually require the value of the potential at this one, and then divide this by h. Okay, so once you have done this thing, right, now what you have to do is to subtract the two, right? So when you subtract, so let's call this as a, call this as b. Okay, so what you need to obtain for del square v by del x square is a minus b. Okay, so when you do that one, you see that del square v by del x square has been approximated. So this is at y equal to y2 has been approximated as 1 by h square v of x3 comma y1 minus 2 v of x2 comma y1, okay, plus v of x1 comma y1. So this is what you are going to obtain, and similarly you can show what will be del square v by del y square, right? So in this case you have to keep this del square v by del y square fixed at say x equal to x1, and then you will have to rewrite the equation accordingly. Okay, so going back and isolating only the points where we have looked at, you see that there is a point at x1 y1, and then you have x1 y2 and x3. So we will call this as x1 y1, x2 y1, and this is x3 y1. So we look at only the points which is required for writing del square v by del x square, and you can see that I am trying to evaluate them at this center point. Okay, so I am evaluating this one at the center point, and I have to give a weightage of minus 2 here, a weightage of 1 and a weightage of 1, and then I have to sum up all these values and then divide the entire thing by 1 by h square. Okay, So you can see that while I am looking at del square v by del x square, y is a constant, y1, y1 and y1. It is x to the right and x to the left that needs to be added up here. Similarly, del square v by del y square at this particular point, okay, in the plane, let us say instead of x equal to x1, we will take the plane at x equal to x2, can be written as 1 by h square v of x2 comma y3. So this is now at the top and the bottom where I have to apply a weightage of +1 and +1, while the center point will have a weightage of -2. So I will have v of x2 y3, which is at the top, minus 2 v of x2 y2, okay, and then plus v of x2 comma y1. Okay, now that I have from the top and the bottom, so let me redraw this grid out there. Okay, what I want to show to you is that these are the points which are actually necessary for me. So this is the center point, okay, which comes in with a weightage of -2. So these points come with a weightage of +1, +1, +1 and +1. So this of course is not just the only points that we have. The grid is uniform everywhere in x and y. I need to look at that one. If I go horizontally, then I obtain del square v by del x square, and if I go vertically, then I obtain del square v by del y square. Okay, so horizontal and vertical direction movement actually gives me that whatever the corresponding partial derivative that I am looking for. Okay, now the condition that we need is del square v by del x square equals minus del square v by del y square, correct, at any point x and y that you are considering, such as the red colored center point over here. The derivative when you go horizontally must be equal to the derivative when you go vertically. So when you actually add them up, couple of terms will actually add up nicely, okay, and couple of terms will not add up nicely. So this is actually x2 and y2, and here I have x2 and y1. So now I can add or rather subtract the two expressions over here. So this is I am going as this one, so I get x2 y3 and x2 y2 and x2 y1. So now when I add up all the terms and then apply this particular condition, what I get is v of x3 y2 plus v of x2 y1 or rather y3 minus 4 times v of x2 y2. So this is x2 and y2, so this is y1, this is y2, so this is x2 y2, so it would be minus 4 times. I have done it over for this one where this would have been the y1 case, but I didn't do it, so I messed up the formula slightly. But at the center I am looking at y2. So now this fellow and this fellow will add up, and all the others are adding up in this way. But since there is a -2 and a -2, this becomes -4. Okay, then I have plus v of x2 comma y1, and you have plus v of x1 comma y2. This is equal to 0. So you can rearrange this and write this as v of x2 y2, which is the center red dot which I have considered. So at that point this is actually equal to 1 by 4, okay, v x1 y2 plus v x3 y2, okay, plus v x2 y1 plus v x2 y3. Okay, so this v of x1 y2, where does this point lie? This point lies here at x1. This actually lies here at x1 y2, right? So this would actually lie at x1 y2, and then I have so this is x1 y2, this is this is actually x3 y2. So x1 y2 is towards the left of the center point, and x3 y2 is actually towards the right of the center point. So you can actually write this as v at the left plus v at the right, the potential at the left and the right, plus the potential at the bottom and the potential at the top. Okay, so what you see here is that, and divide everything by 4. So what you see is that if I am there at the center point, okay, so this is my center point out here. If I want to know what is the potential here, so if I want to know the potential at this particular point, all I have to look to is to the point at the right, point at the left, point or the potential at the top and the potential at the bottom, and then add all this. The average of these 4 will be the potential at this particular center point. Okay, so this is your finite difference method of solving Laplace's equation. These equations can actually be properly coded on a computer, as we will discuss in the next module, but for this module you have to understand that the potential at the center will always be equal to the average around the points. How do I deal with the edge condition? For example, on the edge, if I am trying to find out the potential here, I do not have any right component, right? So I do not have any component out this side, so this is actually missing. So there are ways of extending this formula to include an exterior fictitious point and then represent that, or write this one in terms of the other points and then adjust the solution, or simply recognize that you are never going to change the boundary conditions on the boundary itself and then keep them fixed. That is, you evaluate your problem. So this is a trough problem that I have. So these are the points where I have a grid at the boundary itself, and these are the points where I do not have the grid here. So let us say these are the grids that I actually have at the center. So if I am evaluating this one numerically, I never update on the boundaries. Okay, so on the boundaries I keep them fixed. I iterate or update only in the center of this trough or center of the region. Okay, this is one method of solving. There are other methods, as I told you. You can use an exterior fictitious point and then write down that point and then extend the solution, but those are slightly complicated things which I would not like to consider. Alright, we overran this module a little bit. My idea was to also show you how to code the algorithm or how to write the algorithm and show you the numbers actually. I would like to do that one in the next module. In the next module we will also look at another numerical method, okay, called method of moments. Until then, thank you very much.